Switch over.
So welcome back. So next speaker will be Olga. She's a local female, and she will talk about models of computation.
Thank you, Peter. The usual disclaimer applies. As we heard in the previous talk, it's not meant specifically for the experts in the field, who are plenty in the audience. So they, ideally should bear with me. Yeah, I hope they will. However, feel free to ask any questions. I am not the world's authority on many of the things that I will mention. I do understand this to a degree, and I hope to understand this area better, along with, obviously various other things we'll learn in this program. So, so keep this in mind. Okay. All right. Here we go. So don't be shy. Ask questions. I will assign homework as well, which will be very basic. But let's. If you're not seen any of this stuff before, of course, the idea is for you to look at it and try to solve these problems. Okay. So in the first talk today, I will be mostly focused on the more numerical stuff. And in my second talk, I will be talking more about complexity measures, ways to understand complexity, ways to connect complexity, specifically of matrix multiplication with the tensor notions, although I'll not go into tensors per se, so I'll try to kind of create this bridge between the more abstract and the more concrete. So that's the plan. But for now, I'll focus on mostly numerical aspects of what we plan to do in this in this semester. Okay, so what are the most basic models of computer arithmetic? There are additional models that will not be referenced on my in my presentation, and there are exotic models obviously out there which are a little bit less accessible. So I'll focus on the absolutely sort of bare minimum of what one might need to know about models of computer arithmetic, and I'll start with fixed point. Fixed point is perhaps not as popular as it once was. This is historically perhaps the first model that people considered, and the idea was to look at basically a certain range of values and try to represent them the way we usually compute, when we compute monetary amounts, typically it's within a specific range. Typically they don't go to infinity. And when we compute those, we indicate, dollars and cents, for example. And that means 2 decimal points and however many positions you reserve for the digits before your decimal point. So that would be fixed precision. And effectively what you see here is the exponent that will occur a lot in floating point arithmetic and then floating point number representation kind of happens to be frozen. So you don't play around with this, you don't change it. So unlike fixed point, in the floating point arithmetic, you have more of a dynamical range where you have your numbers represented as follows. You have a sign, plus or minus. You have digits followed by a certain base raised to an exponent. And typically, because we do most of the stuff in binary, your base is going to be equal to 2. However, again, you can do other things. And there, you still have a discrete set of values, just as before, trying to approximate the continuum of all our possible values that we might want to use in inputs. I'm talking reals for now, although you can, of course, go to complex numbers with just the increase in dimension. And there, you have kind of more room to play with. And I'll talk a little bit more about floating point in the slides that follow. So what else? What else do we do these days? We mostly work with 32-bit or 64-bit arithmetic, although, as we heard, perhaps if you participated in the workshop last week on hardware, there are advantages to going to fewer bits and in specific hardware and for specific configurations, for specific tasks having to do with AI, especially today, but going beyond AI. Sometimes it's advantageous to go to 8-bit or even 4-bit representation, and that way you have fewer bits, but then you can compute a lot faster if that's your task you're interested in. But sometimes you don't need so much precision, but then you can benefit by using fewer bits. So again, more of this to come, and Jim Demmel certainly will mention some of that, I hope, in his talk. And then obviously there are experts on this, much more knowledgeable than I am. Okay, what else is out there? There is integral arithmetic, which could be a slightly controversial subject for some people. However, it exists, and as a method, it also can be used theoretically. It can also be implemented practically, although exactly how is a tricky sort of business. So I will not say much about this. I'll just say that numbers in that model are represented by intervals which are meant to contain exact values. And then as your algorithm keeps performing operations, obviously these intervals change, and sometimes they keep growing, so much so that you have to worry about the growth of these numbers. But likewise, in floating point, that's a major concern, and we'll get to this in a moment. So it's kind of two sides of the same coin. However, some people swear by integral arithmetic, some people despise it. So I'm neither of those. I think it's an interesting, model. It has its place. Sometimes it's very useful. However, floating point is the current sort of standard computing paradigm.
So the main disadvantage is that it's slow?
Well, it's just hard to implement well, primarily. But maybe Jim can say more.
Pessimistic very quickly.
Gets
the interval grows exponentially in
yeah.
lots of algorithms.
Oh.
Yes, and the intervals grow out of control typically, so then you get a very kind of ineffective bound on your answer.
So you might come up with use different algorithms than you'd use in floating point.
Absolutely, absolutely. So sometimes you might want to, you might get lucky with integral arithmetic, but usually you do not. Exactly.
In interval arithmetic, you still have to somehow store A and B, the numbers, right? So
you do need to get this bound stored. Absolutely, yes.
So
Absolutely.
then we are back at the same problem, right? So it's either fixed point or floating point for those.
Well, exactly how you implement that, again, typically you can emulate this to floating point, and then, yes, you're back to floating point. Exactly. So there are proposals how to implement this differently. They exist. However, again, this is not mainstream. This is not what I will be mostly concerned in this talk. Okay. Last but not least, you can, in an ideal world, everything is exact, right? And I will say a word that in an ideal world, you can think of real arithmetic being exact and consider getting exact answers. However, reality of computing does not support this contention. But if you're dealing with large integers, first of all, they are representable exactly up to a degree, right, within a certain range. The more your precision is, if you do computations in double precision, you can represent a certain range of those exactly. So this is sort of good news. And again, this speaks to how you actually implement this. In theory, you can keep increasing the size of your words that you will be using for such computations, and then in theory you can keep obtaining more and more digits of your integers, and that's the foundation of the symbolic computing that I think many of you are familiar with. Again, with the disclaimer that I'm no expert on this, I'll just need to mention this for sure because that's an important part of what we will be talking about here. Okay. So, arrows. The arrows in computation come in different guises, in different forms, and for different reasons. And I'll just say a few words about sources of errors that we will encounter as we try to compute stuff. Okay, so there are different sort of scenarios under which you will introduce errors. And you will introduce them inevitably, again, unless your computation is particularly simple, you're dealing maybe with exact integers, and your output is going to be an exact integer or something of that sort. Otherwise, you are going to be introducing errors. So what happens there is, first of all, representing numbers other than those that are exactly representable in your particular model is a problem. So you will always introduce an error just by trying to represent a number. And then obviously you want to pick the nearest number which is exactly representable within your system to your true input, if you know it, right? Sometimes you do not know your true input. Sometimes you only know it up to a certain degree, and that's uncertainty in your data. And also, as you keep computing, if your algorithm performs many intermediate computations before it outputs something, then at every stage of the computation, you will introduce those intermediate errors. I should note that these are not random. There is one of the misconceptions that people might have that, by computing stuff, you will introduce random errors. Theoretically, it's an interesting kind of model. You can play with that, and you can entertain the notion that your errors are random. However, in practice, they are not. And actually, the accumulation of error is what is at the core of the study of numerical analysis, and then error bounds that people are very keen to obtain. Yes?
So on the latest standards committee for floating point, we're probably going to introduce stochastic rounding to make the rounding errors random.
Fantastic, yeah, that would be fantastic. Yeah, so far they were not quite random, exactly. But maybe they will be more random in the future. And there are advantages and disadvantages to randomness, obviously, right? So again, this is a huge subject, and so I'm going to just barely scratch the surface here. And I'm just going to say that people believe, again, maybe kind of an a priori belief some might have when approaching this whole world, is that errors propagate by kind of getting large sums of tiny errors and then leading to instabilities and leading to answers that are far away from true answers. However, what happens in practice is often that a few large errors accumulate, or specifically a certain process that you are performing leads to a large accumulation of error, as opposed to other situations, other cases where errors do not really accumulate. So one has to kind of be careful, and then again, there is art and science to how you kind of try to optimize your algorithm per se, how you tweak your algorithm to try to prevent errors from accumulating. And again, that's a whole big world out there. Okay, so as you see, rounding errors just per se, if you are within some reasonable range, are not going to be huge, but as you progress, you can get to significant instabilities, and we will try to see how this happens here. Okay, so what are error measures that we'll be using? Very, very basic error measures. So you can look at what's called the absolute error, and that's the deviation of your true value from your computed value, or rather I should have said it the other way around, the deviation of your computed value from your true value. Here I'm just talking scalar values. In a second I'll be talking about other things. Okay, is this a satisfactory measure? You might say not really, because for one thing it doesn't scale, right? For a small value, deviating somewhat from the true value, you will get a small absolute error. However, this might not be an honest measure of sort of the mistake that you've made. And so a more accurate measure that is actually going to scale correctly, right, is going to be invariant under scaling, is this relative error. which then will be undefined if your true value happens to be 0, and that would be an exceptional case or something to handle specifically within your again, specific arithmetic. So there, what you see is two kind of slightly different definitions, which are the same. So either you look at the difference, the absolute value of the difference between the computed value and the true value, and divide by the absolute value of the true value. Or you can say, well, your computed value is actually equal to the true value up to this factor 1 plus little rho, and then you want to bound the little rho in absolute value, and that's going to be your relative error in this scenario, right? So however you want to think of this is the same thing, and you can notice that then it scales. If, of course, both x and x hat scale by the same amount, then your relative error will be unchanged. Okay, so let's talk a little bit about significant digits, because that's an important these are important words in that world. And so we'll say that, first of all, what these are the first non-zero digit of your number and all succeeding digits. Okay. So for example, if you have 1.7320 written as it is, so 0 is there, okay? Then you have, 5 significant digits, starting with the first non-zero and counting all the way. Okay, and then if you have 0.0491, then you ignore the leading zeros, obviously, right? They do not count. You start counting at 4, and then you get 3 significant digits. Now, what on earth are correct significant digits? Okay, let's talk a little bit about this. So you'll say that x hat, which remember is an approximation to the true value. That's the computed value typically, or approximate value, or something that represents x, right? So x hat has p correct significant digits if x hat and x, the true value, okay, round to the same number of p significant digits. This is a slightly problematic definition, however. Those in the know will tell us why, and so here's a little example. There are many, many examples like that you can think of. So what happens here? Why is this slightly problematic? So imagine you have the true value x being 0.9949, and x hat, the approximate value, the computed value, whatever it is, being slightly different. So they're not far apart, right? The other one is 0.9951. Now notice what's going to happen. So if you want to round x, it will round, so let's keep the first 2 digits, right? We'll have 0.99. X hat will round to 1.0, right? And now you can guess what that means. So that means that x hat technically doesn't have 2 correct digits. X hat does not have 2 correct significant digits. That's kind of weird, right? Because x hat has 1 correct significant digit, and it has 3. So that's a little bit of a weirdness introduced by this definition. And you can see why this is going on, because obviously, due to the mysteries of decimal representation, right, we passed the threshold here, right? 1 is just above the threshold when it gets rounded up. You get a different digit representation. You then obtain something which ends with 0, 0, right? As opposed to in the other case, you obtain something which is still 0.99. Okay, so this is kind of idiosyncrasies of the decimal system, but in any base, you'll have such phenomena occurring. And so that's a slight problem. You can adopt a slightly different definition. This is definition 2, where you can say, okay, x hat should agree with x, okay, to p significant digits if we look at the difference, take the absolute value of the difference, and then that absolute value of the difference is less than half a unit in the p, so they're half a unit apart, right, in the pth significant digit of x. So now we're splitting hairs here a little bit. I should mention right now Velvel Kahan, who is a world expert on floating point and much more. And so he worries a lot about getting correct digits in numerical algorithms all the time. And so he can give you lots of, probably a 4-hour lecture on correct digits here. Okay, but that's not the purpose of as much, this is fascinating. Let's not get hung up on this. So I just want to say that this whole notion is perhaps a little bit less useful and a little more base dependent, right, than the notion of relative error. So I'll just leave it at that. Okay. All right. So back to our lovely relative error. Obviously, most of the time, and objects we work with are not scalar objects, although that will be the case as well. We want to work with arrays of matrices, arrays or matrices, vectors to start with, which can be thought of single column matrices. We also want to work with tensors, which can be thought of, if it's a three-dimensional tensor, they can be thought of sort of three-dimensional arrays and so forth in any dimensionality. So this quickly becomes an issue. And so for simplicity, let's just talk about vectors for now, because anything can be vectorized. Any more complicated object in this world of, in this hierarchy of dimensional objects can be vectorized. And so for now, let's just talk about vectors. And then we'll say again, we will introduce the relative error in our approximate or computed vector answer x hat by comparing it to the true vector x, to the true value of x, by taking the difference, taking the norm of the difference, and dividing by the same norm, right? The same notion of the norm should apply by the norm of our vector x. Okay, and here there are some popular choices. There are many, many more. There are infinitely choices, obviously, for norm in your n-dimensional space. But then some popular choices are listed here. So you have the maximum norm, the Manhattan norm, also known as the 1 norm, right? The 2 norm, the Euclidean norm, and here I'm still working kind of implicitly over R, so I'm working with real valued vectors, although, of course, you might want to pass to the complex valued as well. And here I'm taking x transpose x, and then forming the square root of that. That's the plain version of this. I'm not using any inner product duality, big words here, okay? However, of course, you can replace this transpose by star, but this is a modest star, not the star in JM's world. This is just a conjugate transpose, which we can all compute, I hope, right? So any questions on the norms? This is also known as the 2 norm, the Euclidean norm, the Euclidean distance to the origin, however you want to call it. Maybe there are some other names for this. But so these are some of the popular choices. Okay, so for example, if we happen to know that the relative error is bounded by some small number, and so here I just wrote 1/2 times 10 to some negative power, okay, then what does it tell you? It tells you roughly, right, that if you are in the regime where if you're looking component by component, if you're looking at larger components, right, so components whose size is about equal of order, right, roughly equal to the norm itself. And there will be larger components than smaller components typically, unless your vector is really very uniform, okay? So for this situation, you roughly have p-correct significant digits in that particular component. So think about it, right, if that's your bound. But for smaller components, you don't say much. Right? If you've got a bound and you have a large discrepancy between components and some of them are tiny, then you don't really get much of a relative understanding of your error within that component. So that could be problematic if you're concerned with component-wise error, if you really want to make sure that component by component you're getting something good. Something representing the answer, something relatively close, right, to the answer. So this could be a problem. And so you can say, all right, let's go component-wise. And so component-wise, we want to form this relative error. And sometimes we want to have an estimate, an error bound, which is very strict about this, right? And it really maximizes the error bound component by component. So then all components are put on equal footing. And sometimes it's important. In various algorithms, so basically, some people might say, unless you got a component-wise bound, your algorithm is no good. That's a very maximalist, attitude. So again, I don't subscribe to this, but some people might want to push you in that direction. Okay.
It sounds very strong. Are there cases where you can get this component?
There are cases where you can get it, but should you be so lucky? Yeah. This is not typically the case. We'll talk about matrix multiplication, and I'll mention this briefly, exactly what you can get, and then what you cannot get sometimes.
So we have an Act in America paper on this.
Good point. Yes, thank you. Right. Okay, cool. So maybe 2 words about precision versus accuracy. Pardon me. So these words are often used interchangeably and are kind of confusingly replaced by each other. Again, if we want to be accurate, if we want to be precise here, we need to split those hairs. And so accuracy is not precision. So just maybe a few words again about the basic model of floating point. So here I wrote it finally for you. So we have in the floating point arithmetic only the 4 basic operations that are ever performed. Again, you can do other things. You can have fancy hardware that does stuff differently, but I'm talking about the mainstream scenario. And there, every one of your binary operations, all operations are binary, okay, plus, minus, multiply, and divide. And for all these floating point operations, at every time you perform a floating operation, you potentially introduce an error, okay? And here we go. So you get the true result 3 times this relative error per this specific operation. And so here, this value delta, which you will not know and you are typically not going to control, is going to be bounded in absolute value by what's called the unit round-off, also known as machine precision. And there you have a few numbers here. So these are for specific concrete IEEE standards right now.
It's the same for multiplication as addition to you?
It's the same for multiplication as it is for addition, yes, which is fascinating.
Just would have thought.
Yeah, yeah.
There she goes.
Okay, so again, accuracy is the absolute or relative error of an approximate quantity, most likely quantity you want to compute or you have computed, okay? And precision refers more narrowly only to what happens in these basic operations, right? So precision is going to be the accuracy with which the basic arithmetic operations are performed. Okay, so that's this difference. And if you're performing a single scalar computation, these 2 agree. Accuracy is precision, but otherwise they do not agree. And again, accuracy can be much, much, much worse than precision. However, accuracy is not specifically bounded by precision. That's a slightly tricky bit. So again, in specific situations, you can do better than precision.
What's an example of a situation?
Well, you can emulate higher precision, for example.
Oh, okay.
You can always design algorithms so that they emulate higher precision, and that way you will go beyond what is kind of theoretically possible on this architecture.
But is there like a natural problem where it happens without doing that? Without simulating?
Well, what is natural?
Any linear algebra problem.
So again, our Act in America paper has a bunch of examples.
So Jim, thank you. Yeah, there is a paper with Jim Demel, Joanna Dimitri, and myself being authors, and then it talks in great length. It's a 75-page paper, I'm afraid, yes. So if you want to know everything about it.
Another talk.
That's it, yeah.
But I mean, this is something that has confused me. How can you solve a problem whose size depend on n using a fixed amount of floating point precision? Like a dot product. Like, how is it possible?
Well, if you're not limited in the amount of operations you can perform, you can keep refining your answer, right? So even though every time you do it in fixed precision, you can keep refining, right? After you got, the first approximation guaranteed to some digits or some degree of accuracy, right? Then you can then keep refining it and getting better and better approximates. Yeah.
But if you only have, like, for example, 32 digits, then can we get better accuracy?
Well, again, you just stack things together. Even when you have 32 bits for a single operand, then you can always grab a couple more. As long as your machine, has more capacity or has more memory, then you can always emulate higher precision arithmetic. That's a common trick that is used.
Could we prevent the possibility of emulation if we insist on random rounding?
Pardon me?
If we used random rounding instead, we remove the possibility of emulating higher precision and get like a theoretical result there?
I don't think so. Offhand, I don't think the randomness in rounding has to do with, degree of precision. So again, Jim has a comment here.
Yeah, the simulation, the proofs that you can extend precision assume round to nearest even, typically.
Yeah.
So
Yeah. So that is a somewhat orthogonal sort of direction here. Yes. Okay.
Can I ask a quick question? Sorry.
Yes, of course.
So these numbers, that's like something you have to prove holds depending on like how you allocate bits to the exponent and how you allocate the mantissa.
These are the numbers that the good folks that create computer hardware and those who create standards for it have to ascertain the hardware satisfies. Yeah,
Okay.
absolutely. So if you're a hardware engineer, that's your task.
And just out of curiosity, like, do you always use the same? Do they just set aside some number of bits for the exponent and some number?
Yes.
Yeah.
That is correct. Yes. Yeah. So again, for the intricacies of exactly how it's done in iron, right, or whatever, silicon.
proposals for variable precision, which use more exponent bits for very large and very small numbers, but they haven't gotten any traction. Sure.
And they'll say a couple of words, but again, it's fascinating what is done right now versus what could be done. Again, there are various directions in which you can kind of go and improve your floating point computations, should you be so inclined, but it's very expensive. And again, manufacturing hardware at scale is the issue here. Because if your hardware does not agree and does not function well with somebody else's software, then this will be a problem. Okay, sorry, my computer lost track. Speaking of computing. Okay, so backward and forward errors. Again, very, very basic general introduction here. So suppose we have computed something, and we want that to represent the true answer. Okay, what does that mean? How do we measure the quality of what we got, the quality of our answer? So we have the true input, which we will call x, the true output of a function that we are trying to evaluate, which we'll call y, okay? And we have computed some y hat, and we want to understand how far is the computed answer from the true answer, okay? And so again, you can say, well, we can take the absolute difference between the true answer and the computed answer, and that would be the absolute forward error. Or we can take the relative forward error, where we'll take y minus y hat, take the absolute value, divide by the absolute value of y. If y is a vector, and of course, if y hat is a vector, then you use the vector norm, as we previously discussed. Okay, that would be the forward arrow. Okay, what on earth is the backward arrow? The backward arrow is motivated by a slightly different question. So you might wonder, for what actual value, for what possibly slightly perturbed value of the true input did you compute the correct output, right? That is your question. And so that introduces the notion of backward error. That means for which, again, I will just repeat, for which perturbed data x plus little delta x, hopefully little delta x, do we have y hat, which is f the exact evaluation, right? The exact evaluation of f at this point x plus delta x. So maybe it's time to draw a little diagram here.
What if y hat is out of the range at f?
You can still look at the, completely out of the range. Yeah, you pretend this doesn't happen, or you artificially extend the function value. Again, in theory, this could happen a lot. In practice, then you just say, again, you need to know it somehow, right? You need to know somehow that this is out of the range. So this becomes a more ideological issues, like how you determine these things within your algorithm.
F is typically solve linear systems. So
Yeah. Yeah, so for our purposes here, think about solving linear systems, think about transforming matrices to other matrices, matrix decomposition. I'm jumping a little bit ahead of myself, but we'll talk about this soon. And nothing like that would be a concern specifically, but of course, yeah, theoretically, it might be a concern. And
So imagine in diagonalization, if you output something that's not invertible, that's what you imagine.
let me try drawing a little diagram. So here's x, okay? So theoretically, it should go to this point y, which is the value here, f of x, right? Instead, what we computed is y hat, right? And so what we want to determine is from which perturbed value of x does this come, right? So this is sort of the little diagram here. So this is this point, and so we want to determine this sort of deviation here, okay? And let me make it a little bit different. So here I'll draw a little dotted line or just a little blue line, okay? So there is a distance between x and delta x, and there is likewise some distance between y and delta y. So which one is forward and which one is backward? So you can tell me, of course. Your computation sort of goes this way, right? So your computation sort of from x, which is not well represented, not perfectly represented, you will somehow get y hat. So x is not really x, okay? So from this inaccuracy in x, possibly, or maybe x is exactly represented, but you still get y hat. That is a typical scenario as well, okay? Anyway, y hat, you imagine, is the output of this precise function f at some slightly perturbed value. So where is forward error and where is backward error?
When are you interested in this backward error?
Oh, you're interested in this a lot.
This is the gold standard for linear algebra. So is your algorithm backwards?
And the more will follow. I'll talk a little bit more about this, yeah.
Okay.
So just show me where forward is and where backward is, and then we'll move forward. Yeah, where's forward, where's backward? On the right is forward error, right? On the right is your forward error. The difference between y and y hat is sort of on the right side of this diagram. So here you go forward. Right, forward error is located here, and then backward error is located here. For specialists, you can say there is another kind of error you might throw in. So what would that be? Okay.
Like mixed forward backward error? Because actually what's written there isn't exactly forward error, right? Because forward error should be y hat equals f of x plus something.
Oh, right, it's the diet.
I thought in forward error the input has to be x, and you just measure the change in the output.
We are measuring the difference between the computed value, however it's computed, right, and the true value. But the true value should come from the true value of x.
Right, so that's what I meant. Like in the forward error, you probably mean delta x equals 0, right? In the forward error.
Well, the forward error is this distance, right, between the true value and the computed value.
But it has to be the computed value on the true input. Otherwise, it's mixed forward backward.
Well, f is not the algorithm, it's the
We don't have
function.
it, right? We don't have
It's
it.
just an illustration. Y hat is what she measured.
we are seeking, so here to go backward, right, we're seeking an adjustment to x so that we will precisely get y hat.
I think the confusion is it's no computed value.
There is no compute,
It's
right.
just an F, it doesn't do any
Yeah,
mistake.
f does not exist in the machine, right? There is no magic way of computing most functions that would be precise.
Maybe you should say y hat equals alg of x.
Okay, yeah, good point, good point. Yes, so there is no, for most functions and formulas out there, right? What you will compute will not be the true value on your input. And that's what happens here. Yes?
What happens if f is not injective, so delta x is not uniquely determined?
We're okay with that, provided we can still guarantee the nearness, right, to the value of x.
Can I make a comment? So,
Of course.
you know, I'm not originally from numerical analysis. It took me some time to understand this. But I think now I understand backward error, and it's very, very ingenious idea due to Berkeley. Very ingenious. And but it's a theoretical concept. So
Yeah.
I think the point is, when you compute, you start with x, and there is this computation. Every step there is an error, error, error. It's very, very complicated. But now you say, all these steps, all these many errors, subsume them in one thing. Just to say, close to x, there is another x
Value,
plus delta
yeah,
x.
yeah.
And now starting from x plus delta, if you could compute without any error, then you get what the machine spits out.
That's right.
Of course, it's very difficult to do backward errors, but if you have such an analysis, then you are in very good shape. So I think it's very ingenious.
Could it also be not surjective that there is no such delta x such that the computation would have been correct?
So that could be, and that in that case, so let me redraw this diagram in case you wondered. So this might be the situation. So for all of you who are interested here, right? So you can say, let's look at this. Maybe this does not happen, then we have three values, right? Maybe we'll have y hat, and f of x plus delta x. So that could be your situation as well. But again, in the usual backward error scenario, we do want to find some delta x so that x plus delta x will be precisely equal to y hat. So I could draw all three if you'd like. So you got somehow y hat. Then of course that's your measure of your forward error. And then maybe you have another one which is f of x plus delta x. Okay. And so then you might wonder, okay, maybe you can only guarantee some nearness of that value, right? So here you can have a bound, and then there you have a couple of bounds, and then you can therefore estimate your error. That's a possibility as well. So yeah, maybe I should have said this. So that's the true function rate going across. Let's do this. Okay. Okay, so in backward error analysis, we seek such an understanding, right? We seek to find x plus delta x, or this delta x that would lead us precisely to the value that we can obtain, our algorithm can obtain. And this is usually an intricate business. This is, as Jim mentioned, that's the golden standard of numerical analysis. And when we obtain a guaranteed backward error, which is roughly bounded by data uncertainties in the data, we consider this acceptable. Right? We consider that we've achieved what we could possibly have achieved, and so this is kind of the end point of this error analysis, which leads to a satisfactory conclusion. You might, again, should you be so lucky, If you're so lucky, that's your error analysis. If you carefully performed stuff and that's the conclusion you got, then that's the stopping point. You say, okay, great, this is a great algorithm. It performs fantastically well. And so there is non-trivial perturbation theory. You usually need to perform along the way for this to actually happen. And sometimes your algorithm is not going to be backward stable, right? It's not going to give you this numerical error in the backward direction that you can be happy with. And such is life.
So, sorry, I'm still having trouble wrapping my, I mean, everyone in the room who's familiar with this seems to think backward error is gold standard. And, you know, if you could do that, everything is wonderful. But I'm seeing this roughly for the first time. And I'm not seeing it. So what am I missing?
Can I give a stat?
Of course, yes.
So there's a real struggle to understand how algorithms perform on problems that are either kind of sensitive to perturbations or robust to perturbations. And we might use the same algorithm for both classes of problems, but we'd have very different expectations for how the algorithm should perform on those. And it's differentiating between how an algorithm performs on a problem that's very robust to perturbations versus what we should expect of that algorithm on a problem that's inherently sensitive to perturbations. And so backward error gives us a way of saying the algorithm does a good job, does the best job we could expect it to do, given that we're working with uncertain input, and that uncertain input in a problem sensitive to perturbations naturally will give, can't be counted on to give a robust close.
And forward error does not give you that information.
Right, forward error would mean the output of the algorithm was very close to the exact answer that we seek, whereas backward error would say the algorithm gives us the exact solution to a nearby problem.
But is it correct to say we would all be happy if we could prove forward error bounds all the time? They're just hard to prove. So like when we say it's the gold standard for JM, like I guess it's the gold standard, it's often the best you can do. But of course, if you knew you were getting an absolute, am I wrong on that? If you knew you were getting a good absolute relative error, you'd be
it's just
much happier with that. It's unrealistic. But like gold standard,
not just because it's hard to prove, but because it's hard to achieve.
It might be impossible to achieve, yeah, but it's like you would want it if you could achieve it. It's just that maybe backward error is the best realistic thing we can hope to achieve for many problems.
Right, and as long as you have a condition estimator to go along with every problem, which we try to provide in libraries, then you can get the forward error bound if you want it.
Yeah, if you could bound the conditioning, yeah.
Yeah, and there are condition estimators which work with high probability, et cetera, too.
But I guess the setting that he was saying was that the input itself is noisy. So then, like proving a forward error statement, like then you're eating up the noise. It seems like less valuable than backward error.
I mean, I think the reason you're confused is if you're doing representation theory, the answer is not stable to perturbation, right? And in that situation, forward error is the correct notion.
And there are situations which are very unstable under perturbations, of course, and yeah, we'll see them very, very much so. So maybe I'll try to kind of circle back to this if I could, if I can, and of course, happy to discuss this further. And again, I think there are people in the audience who are very knowledgeable about this, who can discuss it in greater depth. Okay, so again, remember backward stability. What does that mean? That means that our method, our algorithm for computing some function, typically, right? We'll just keep calling it f, is going to produce the exact answer on some slightly perturbed value delta x, and this is going to happen for all inputs x in your intended domain, okay? So here we'll say for some small delta x, what is small is in the eye of the beholder. So you might have different guarantees, and so the definition of small is up to you, basically, right? It's very much context dependent. You can say what you mean by this. And what many algorithms satisfy is this kind of slightly tweaked version of what we saw before, and that will be y hat plus some little correction delta y is actually f of x plus delta x. So back to this diagram, there is a difference, right? There is a difference now, so good that it's there. There is a difference between the value you computed and the value on some sort of perturbed, slightly perturbed value of x. And that difference is now delta y. So this is our lovely delta y, which appears here. So you can now bound delta y by some hopefully small constant times the measure of the size of y, so the norm, the absolute value, whichever you like. And then likewise, delta x is bounded by some kind of constant you control times, hopefully small, right, times then the length, the distance of x to the origin, the norm of x, the absolute value of x, again, some kind of measure of size of x. Okay, so this is typically what you will see. This is a, again, not every algorithm will satisfy this, but this is a very common notion that you will encounter. Okay, and interpretation here is y hat is now almost the right answer, right, for almost the right data. So not great if you're always thinking exact, right? If you're you know, an abstract algebraist, perhaps that's not so exciting, but this is real world, and this is what happens in real world. Are you okay? Are you okay with that? Okay. Okay. All right. So numerically stable means it's stable in this mixed sense. Okay. Numerically stable means stable in this mixed sort of backward, forward, backward sense, as described here. Okay. And we'll say forward stable if it, again, this is a slightly interesting definition, forward stable if it actually produces outputs with forward errors of similar magnitude as those that are obtained by a backward stable algorithm. That's a very bizarre sort of mouthful definition to give. Maybe there are better ways of describing it. And just to confuse maybe JM a little bit more, I want to say, imagine you can, imagine you're just using Cramer's rule on 2x2 matrices. And well, for simplicity, imagine you can compute their determinants exactly. Then you're going to be in this situation. You're going to have this forward stability, even though your algorithm is actually not going to be backward stable. It's kind of bizarre. I mean, I'm not assigning this as an exercise, but if you want to be challenged, that could be an interesting one. Okay, so there are situations where this happens, in other words. Okay, so yeah, to end this little bit of discussion, I want to quote the handbook for a calculator, which says, backward error analysis is no panacea. It may explain errors, but not excuse them. So says Hewlett-Packard. I just thought it was a good quote.
One question is, f supposed to be an idealized function that the algorithm computes?
F is an idealized function, something like sine, cosine, tangent, you know, the exact largest singular value, and so forth.
So one good example for mixed stability is solving the symmetric eigenproblem. One of the outputs is an orthogonal matrix, but it won't be exactly orthogonal on floating point, but it's very close to orthogonal.
Is there a reason we don't just define forward stable as the alg of x is close to f of x?
That's what it, well...
here it says something more.
It says something more, right? It says, see, the notion of how close needs to depend on your input. Again, you cannot just say, well, just uniformly close. Uniformly close is not a good measure.
But we could do epsilon times norm of the input, like you're saying.
But then you're back to the input, and then you can say that.
But this definition refers to backward stability in the definition of forward stability. I'm just asking why there isn't a self-contained definition of forward stability that just says alg of x is close to f of x in relative error.
Because there's a condition number that has to come in.
Which will come in on the next slide.
Yeah.
Got it, okay.
Okay, no worries. Okay, so let me give you a couple of exercises, and then we'll talk about conditioning, and we'll wrap it up. Okay. There was a non-existent exercise where we were counting digits which were correct or incorrect. So I assume everyone here has already done this exercise. So here are a few more exercises. The first one is very simple as well. So sometimes instead of measuring relative error the way we did before, we can decide to divide not by the absolute value or the norm of x, this magical true value, but instead we divide by something we actually get a hold of, which is in our hands, and that's the absolute value, the norm, the size of x hat. So that's usually more accessible to us, okay? And then there you can obtain inequalities between this measure of relative error and this slightly more idealized measure of absolute value, relative error. So this first exercise is about obtaining these inequalities. Okay, it's quite simple. You should be getting this fairly simply. Okay, now here comes a rather, again, straightforward question. So you are computing 2 by 2 determinants by the usual formula. So straightforward, completely clear calculation, A11 times A22, right? The entry which sits in the upper left corner times the entry which is in the bottom right corner minus the product of the other 2 entries, A12, A21. And the question is, very basic question is, so is this going to be forward stable? Is this going to be backward stable? Is it going to be numerically stable in this notion that we introduced? Very, very basic stuff. Okay, then moving on to slightly less basic questions. If you are a computer software engineer, give me a stable way of computing square roots for complex numbers. Okay, so you have complex numbers represented as pairs of real numbers, and I want you to compute square roots in a stable manner. How would you do this? Okay, and last but not least, suppose you want to run a continued fraction computation. Does everyone in the audience know what a continued fraction is? A continued fraction is sort of a chained fraction, right? So not just a numerator over the denominator, but a numerator over the denominator, which begins with a value and then continues into plus another fraction like that. So it gets very big pretty clearly, pretty easily. And so here we're kind of computing it backwards, which if you think of it is the natural way of doing it. Okay, so what do? We have n plus 1 values, which are called a's and b's. Actually, the n plus, so these are not exactly 2 times n plus 1. These are actually, so not 2n plus 2, it's 2n plus 1 values. Okay, so you start by taking the very last in that sequence, the a value, indexed a sub n plus 1, and then you start performing the usual recursion for computing the continued fraction. So you go backwards. This is a bit of MATLAB notation, right? So you go from n to 0, but you go backwards. This is your step size minus 1. So I took the liberty of using a little bit of MATLAB notation here. And then you go qk is now set to be ak plus bk over q, the previous one, which is actually further to the right if you think of it, divided by qk plus 1. And so after running this, you end, and you will obtain the value of your continued fraction. And the question is this going to be OK for numerical purposes? In other words, is this going to be a stable algorithm? What kind of error bound? So I'm just asking you, give me some error bound. Give me an error bound, right, for this algorithm done exactly like this. And then if you give me an unusual one, that would be great, but probably it's going to be the same error bound if you just analyze this. OK. OK, so now a few words about conditioning, and we will wrap it up as promised. OK, so what on earth is conditioning? Conditioning has to do with the issue which we identified in this lively discussion, namely sensitivity to perturbation. So this is an interesting and important aspect of your computation, of your algorithm that you typically are concerned with. And so here, what we want to say is, again, we computed some value. We want to understand how close it is. And for simplicity, let's just try an error analysis and try to see what will come out if our idealized function is something which is, let's say, twice continuously differentiable for simplicity. So think sines, cosines, whatever your favorite function is, which is twice continuously differentiable. I bet most calculus functions are. And so then you start looking at the difference between y hat and y and saying, OK, y hat is, again, per hour backward value assumption is f at some x plus delta x. Okay, so let's subtract f of x from f of x plus delta x. And now we can use Taylor's theorem because we assumed twice differentiability. Okay, let's work with that and see what happens. Okay, so then we go y hat minus y. We can divide it by the true value, right? That's the relative error on the forward side. Okay, we were approaching that. And then here we'll just rearrange things slightly. So we'll say, okay, what's going on? We already have f prime times delta x. Let's just rearrange this a little bit. We'll say, okay, this is going to be xf prime over f. And you will see why these contortions are happening, because I want to introduce the relative error here as well in x, right? So this is delta x over x. And this quantity will stand in front of that relative measure, correct? And then, of course, you have big O. If we assume twice differentiability, then we'll get big O of delta x squared. So far, so good, right? Nothing fancy. Nothing fancy has happened. OK, so surprisingly, this quantity has a name. This is precisely what we call the condition number. And then I introduced it in this basic scenario where we have twice differentiability to kind of motivate where it comes from. So it comes from our attempt to understand this relative error rate in terms of this relative error and single out the most important term that will determine the scaling. So very roughly, you can see this will be basically that quantity. If you have a bound on this quantity, then you will get a bound on the error here in terms of the error in your data, right? And this quantity. And so not surprisingly, this is what's called the condition number. Okay, we'll get to the point of, yeah?
If these are vector values, do we take norms of everything?
So, of course, you will take norms, and more than that, we'll talk about matrices in a second, yes. So, as you see already on this baby example of a scalar valued twice differentiable function of a scalar, possibly vector, I don't know. Let's say a scalar input, a scalar variable. This measure actually does correspond to how much, relatively speaking, you will change the output as a multiple of the input, the relative error in the input, right? So basically, it measures the relative change in output for a given relative change in the input. Okay? Okay. And here's a very basic example. So if you take the logarithmic function and try to understand its conditioning, its condition number, then you'll discover that the condition number is just 1 over log, taking the absolute value. So again, intuitively, I guess this is very clear. As you approach the value of x equal to 1, then your logarithm will approach 0, and that quantity, c of x, this condition number that will occur, will approach infinity. And so what you see is that for tiny changes in the tiny relative changes in x, you will incur sufficiently, really high costs, even in the relative values of y. So your output will kind of react disproportionately to your input. Yeah?
In that basic derivation on the top, are you assuming the second derivative divided by y is order 1? How are you able to get order delta x squared and ignore the multiplier?
So this is just a rewrite, right?
But the second term.
The big O.
The big O, yeah.
The big O is occurring here, right? So we have what? We have divided by y. We are just assuming that the true value is not 0.
Means when you divide it by y, how do you put the second derivative of f over y into the capital O?
This is big O already.
But it could grow as a function of x. It may not be a constant.
We're looking locally, right? We're looking in the vicinity of x. So that's why you're getting big O. Maybe I'm not following the question.
It's not the way theoretical computer scientists use big O.
Just think of x is fixed and delta x varying, and it makes sense.
Yeah. X is fixed.
X is a fixed.
Yeah, no,
right,
but that's that was the.
Yeah, let's do usual Taylor kind of scenario, right? We are in the vicinity of the true value. We're not far away from some value of x. Yeah. So it's not some magical kind of crazy bound everywhere at once, right? that's not what happens here. Yeah. Question? Yes. Oh, time. Okay. Yeah, I'm about to wrap it up. Sorry about getting distracted with all of the machine and so forth. Okay. So as you can see from what we just discussed, the forward arrow is roughly speaking bounded by the condition number, right, times the backward error. That's what we saw. And in the same manner, you can think about vector-valued quantities and matrix-valued quantities, and even n-dimensional tensor-valued quantities. You just need to redefine the condition number accordingly. So for example, for matrices, so two-dimensional arrays, which are square and invertible, so again, to be technically precise here, the condition number is defined sometimes from scratch as the product of the norm of A times the norm of its inverse. And we'll circle back to the question how this is relevant. So for now, I'll just say you need a matrix norm for this to be subordinate to a vector norm. So typically you take something like the so-called spectral norm on your matrix, which is the the largest singular value of your matrix. Can be defined in a bewildering variety of other ways, but that's maybe one definition you might have seen. Or the infinity version of this, but in any case, it's a norm which is subordinate to a vector norm on your space. And why would that be necessary? Because with that definition, that quantity is going to play exactly the same role as the quantity we previously defined for a twice differentiable function, which is scalar valued. Okay, so precisely what does it guarantee? For an invertible matrix A, the condition number as defined here, keep in mind, and with the vector norm, which will be then inducing the matrix norm, the condition number will then be actually a measure of the sensitivity for your solution X, to the linear system AX equals B, to perturbations in the data, which is in your right-hand side, right? Which is your right-hand side B. Okay? And then a little question here, does this basic sort of rule of thumb still apply? That's my last homework assignment. And let me close.
In this last question, are we imagining the algorithm is going from B to X or from X to B?
The algorithm for solving linear systems starts with, it has no notion of X. X is what you need to find. Remember this cartoon? Find X.
So when we say forward error.
So we are always finding X. B is given, A is given, we need X. Yeah. That's what solving linear systems are about. Yeah. Okay, cool. Anyway, just last point about floating point, and I'll shut up. A floating point arithmetic is very intricate, and the standards for it are very detailed. Just to emphasize again what's going on, there are lots of issues just with the representation. As I mentioned already, we have barely scratched the surface in this talk. So for those who wish to learn more, there is, again, a huge variety of information out there. I just put out some technical info on what these values actually are just in the floating point representation. Keep in mind there are exceptional values, NAA, which is not a number, also kind of signed zeros, and signed infinity values. So these need to be incorporated in any standard of floating point arithmetic for this to make sense and to handle exceptional situations. So I'll just end with the quote, actually by Cleve Moller, as told by Michael Overton. So supposedly, Cleve Moller used to advise foreign visitors not to miss the two most awesome spectacles of this country, right? And one is the Grand Canyon, the second meetings of the IEEE committee. So needless to say, it's very complicated. And if you want to learn more, read basically everything on Velvel Kahan's website because he is, amazingly careful about describing all these intricacies. And he has been, as you know, right behind a lot of the IEEE standards and the floating point developments. So here is by no means a comprehensive list. These are just some references that I like. And I wish to advertise the book of Jim Demmel here and the book of Peter Bergesser and Felipe Cooker on conditioning. So that could be an interesting sort of viewpoint, right, by someone who is more a theoretical computer scientist on these issues of conditioning. So talk to Peter, talk to Jim, of course, and read everything on Velvel's page. It's amazing. And thank you.
Because our lunch break is quite short, that we don't take any further questions. We reconvene at 1:15 already, so it's a short lunch break. Thank you.